Okay, so we can get started. Welcome to this session. I'd like to take also the opportunity to thank the organizers and especially Ahmed and the local hosts for this conference and for the opportunity to join. Our first speaker is Clay Cordova.
All right, my mic on? Everybody hear me? Okay, there it is. All right, so I'm going to tell you about the representation theory of solitons. Before I get started, let me give a shout out to my collaborators. This talk is based on 4 papers that I wrote in the past year. I'd especially like to highlight the contribution of my 2 students, Diego and Nick. Nick is out there somewhere in the audience, so please direct all tricky questions towards him. Okay, let's get started with a little bit of motivation. So throughout this talk, we'll be working in 2 space-time dimensions. And let's start by thinking about a scalar field theory. So we have some kind of Landau-Ginzburg model, and maybe it has an interesting potential, which I have sketched here. So here's that potential. So what do you see? It has a leading term, a phi to the 6th term, and if that's all there was, there would be a tricritical point, an interesting CFT at long distances. But we've also activated some lower order terms, some relevant deformation, and the effect of those terms is to gap the system. And in this case, there are 2 degenerate minima, or in the quantum theory, 2 degenerate ground states. And we'll call them omega 1 and omega 2. So in this kind of system, we'd like to understand what are the excitations above the ground states. And there are 2 qualitatively different kinds of excitations that I will focus on. The first are what you might call particles. For instance, a small fluctuation of the quantum field phi above a given vacuum state. And more technically, what I mean by particles in this talk is that the behavior of the field at plus and minus infinity is the same. So same vacuum state. The second kind of excitation is a soliton. Here, a soliton means that the vacua are different at plus and minus infinity. So the field phi interpolates between the 2 vacuum states in space. And one very old fact, which will come again anew here, is that the minimum energy soliton is stable. It cannot deform to a particle excitation. Now, this talk is all about global symmetry. So, of course, if you have global symmetry, you expect some kind of multiplets of particles and solitons. And we're going to see that fact on steroids in this talk. Okay, let's get a little more technical. In this kind of situation, we can look at our quantum Hilbert space, and we can decompose it into sectors. In this case, there are 4 sectors. What do these subscripts mean? Well, they indicate what is the ground state at spatial minus infinity and plus infinity. So we have these 2 states, so we have 4 sectors. And if those labels are the same, then that's the sector of particles. And over here, the labels are different, so that's the sector of solitons. Now, these are super selection sectors. What I mean by that is that if you act with a local operator, it preserves the sector that you're in. So local operators can't move you. Now, how is the interplay with symmetry? Well, we can distinguish 2 situations. One situation is a symmetry which is not spontaneously broken. In that case, it preserves the vacuum state. So it acts on a fixed sector in this decomposition. And a second possibility is a spontaneously broken symmetry. In that case, it permutes the vacuum states, and so it permutes the sector labels here. And one thing I'd like to emphasize about symmetry action on this decomposition is that if you have a standard group-like ordinary invertible symmetry, it will always, always, always map particles to particles and solitons to solitons, but it will not mix them. Okay, so now, given this motivation, let me advertise our main results and questions here. So the question is, suppose the quantum field theory has a generalized or non-invertible global symmetry. We'll call that symmetry C in the rest of the talk. And the question is, what is the implication on the massive spectrum? What are the multiplets? And a closely related question you could ask is, what selection rules does such a symmetry imply on the S matrix of these states? What are our results? So the first thing I'll do is I'll describe to you the math that you need to understand this question, the new kind of algebra you need to use. And the punchline, the results that we'll see, is given some non-invertible symmetry, we'll obtain novel degeneracies. In particular, we will find that non-invertible symmetries have particles and solitons in the same multiplet, and hence with degenerate mass. Okay, that's this equality here. So this reflects the kind of intrinsically strongly coupled or quantum nature of these symmetries. Intuitively, in a weakly coupled model, a particle is much, 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 much lighter than a soliton. But here, we see them degenerate. Okay, enough with the warm-up. Let's get started. So first, let me set the stage. What are we talking about? What is non-invertible symmetry in two space-time dimensions? So symmetry, the first sacred principle of it, is that we have operators that commute with the Hamiltonian. That's what we mean by being conserved. And we will be in the fully local situation of symmetry here, which means that our symmetries will come from topological line operators. Okay? We'll give these line operators some labels, A, B, C, etc. And mathematically, these assemble themselves into a fusion category. This is the notion that replaces a group for us. So in particular, I'll assume a finite range of these labels, A, B, C. And so I'm talking about the analog of a finite group in this talk. Now, just like the group case, there's a multiplication rule. But in this case, it's a more interesting multiplication rule. It's a fusion rule. So A times B doesn't have just one term here, but in general, a sum of other terms with some interesting coefficients. And that's where we see the non-invertible nature of the symmetry. Now, that was when we think about these lines acting at fixed time when they describe operators. We can also think about the operators extended in time. Then they make a local modification of space, and so define a new defect Hilbert space, which will sometimes appear. So in that case, H, the Hilbert space, would be converted into HA. And you could ask, what kind of states are in there? Well, one way to think about that is via the state operator correspondence. So the states in this HA, you could think of them as twisted sector operators. So you have a local thing here, but instead of it just being a standard local operator, it has this long topological tail attached to it. So that's what these twisted sectors are all about. Now, how does the symmetry act? How does it constrain the theory? Well, non-invertible symmetry acts in different ways depending on the spatial topology. So the first question you can ask is, how does it constrain ordinary operators before we get to the particles and solitons? So in that case, the right spatial topology is a circle. And the action of the symmetry is by something known as the tube algebra. So what is the tube algebra? Well, one way to think about it is pictorially. So the elements of this algebra are decorated cylinders. So here is such a cylinder. Time runs vertically. Space is the circular slice. So how are you supposed to think about it? So A is going along in time. C acts at a fixed time, and it converts A to B. And maybe there's some data at the junction that I am suppressing. Okay, so that's a map, C acting from twisted sector HA to twisted sector HB. And these pictures can compose by acting in sequence. That is, vertically stacking them, and then simplifying using the rules of the fusion category. So that's the multiplication rule. So the punchline of this is that there is an action of this algebra on the direct sum of all twisted sectors, all the twisted sector operators there. And in particular, that includes the standard local operators in the theory. And so if you want to know what are the implications of the symmetry on local operators, well, you need to understand what are the representations of the tube algebra. And there is a known mathematical answer to that. The set of all representations of this algebra is what's known as the Drinfeld center of this fusion category. So it's a known mathematical construction, and we could unpack that and learn about all the multiplets. So that's the action of symmetry on operators. So now we're going to do the same thing, but we're going to consider instead the action of symmetry on open spatial manifolds. Okay? So we have open spatial manifolds, but we're in one dimension, so there's not really many options for what that manifold can be. It's just an interval. But the interval can have various interpretations. So there are different contexts here. So one possibility is that it's really what you think when I say an interval, a finite length interval. So for instance, you could be talking about a conformal field theory where you have some conformal boundary conditions on the two sides. That's a natural problem in both string theory and condensed matter, and you could be trying to understand the states there. Another natural setup where an interval is secretly living is when space is R. When space is non-compact, that's the setting for particle physics. In that case, you also secretly have an interval because you need boundary conditions at infinity to define finite energy states. Okay? So that's the context where you're talking about particles and solitons. And the setup that I will describe applies to both these scenarios, depending on exactly the words that you use. I'll focus, of course, on this gap situation, the particle and soliton case. In that case, at long distances, we're thinking about a topological field theory with various different ground states acted on by this symmetry. So that's the infrared, and we're looking above that. Okay, so we need some new algebraic ingredient when we start talking about the action of symmetry on states on the interval. And the new algebraic ingredient is what is called a module category, M. Let me unpack what that notion is for you. So the first pass is that this M is a list of boundary conditions that you have. It's all the possible boundary conditions. We call them little m, little n, etc. And there are bulk boundary fusion rules. So M knows how the bulk symmetries act on these boundary conditions. So here's a diagram, for instance. You have M, here's a boundary, and M is converted into N by the action of a bulk symmetry A. Okay, so that's the data in this module category. And physically, you could think that if the bulk line changes the boundary condition, it is spontaneously broken. Right? And if it does not, then it is not spontaneously broken. And the role of this M is it tells us about the superselection sectors. So we have states on an interval, so we've got a pair of boundary conditions, which means we've got a pair of elements in this module. So the superselection sectors are labeled by pairs of elements in M. They look like this. And when we quantize, we get either boundary changing operators if we're talking about a finite interval, or we get particles or solitons if we're talking about an infinite length interval. So those are the two different contexts for this algebra. Now, we'd like to understand the implications of symmetry, so we want to know how does the symmetry act on those superselection sectors. And it acts by something that I will call the strip algebra. This is the analog of the tube algebra. Okay, so what's the strip algebra? The elements are decorated strips. Okay? So here's such a strip. So you have a superselection sector, HMN, and you should think that A acts, and it transforms this superselection sector, HMN, into HRS. And there's some data at the junctions that I am suppressing. Okay? So this is the analog of the tube algebra. The composition is similar, right? We can vertically stack. We can act in sequence with these. And then we can simplify using all the rules of the fusion category. So we take this picture, and we do some manipulation on it, and we'll get a sum of pictures like this. So that's the multiplication rule in this algebra. Okay? And the punchline, of course, is that this strip algebra acts on the direct sum of these superselection sectors. In general, mixing them all together. And so what we would like to know is what are the representations of this algebra, And can we unpack them? Can we really get to the bottom of what are all the linear maps and the implied degeneracies? So not just an abstract answer, but an explicit answer. Okay, so what do we know abstractly? Well, this strip algebra is an example of what is called a C-star weak hop algebra. Okay? It's supposed to generalize group rings for the invertible case. So there's a lot of words there, C-star weak hop algebra. C-star means it has a dagger, the notion of dagger. That's something you expect in unitary theories. And weak hop algebra, it's not super important to know the definition. What you should know, though, is that it's the kind of algebra where if you look at its representations, you can define duals, and we need that because the duals are telling us that there exist antiparticles. And there are tensor products, and you need that because if you have single particle states, you better be able to construct multi-particle states, and we need symmetry to act on those notions. So that's in one way to understand why we got this structure. It's where we can define duals and tensor products. The second fact is just like the tube algebra had a well-known representation theory, here, abstractly at least, the representations are also known. The representations of this algebra is a certain homomorphism space that involves the module and the fusion category. That's very abstract. We'd like to unpack it and get somewhere specific. So how can you unpack these degeneracies? Well, in any given case, you can compute what this is, and it's very useful to visualize these representations with a quiver or graph. How does this quiver look? Well, the nodes are elements in the module, and you should interpret those nodes as the distinct vacua in the theory. And the arrows are morphisms between the vacua, and how are they interpreted? Well, if the nodes are distinct, then that arrow is a soliton, and if the nodes are the same, then that arrow is a particle. And this is an echo of similar quivers that have appeared in the past. So this quiver diagram is our desired object. It yields the implied degeneracies from the fusion category. And we're now going to see it in practice. Okay, let me do some examples. Let me start with an integrable example. That's nice because the answer is known. We can benchmark our techniques there. So we're going to consider the tricritical Ising model. That's this central charge minimal model. And there are 6 primary local operators and correspondingly 6 topological Verlinde lines we could study. I would like to focus your attention on a particular line, topological line that I'll call W. W is a Fibonacci line. That means it obeys the Fibonacci fusion rule. W times W is 1 plus W. That's an interesting symmetry of the tricritical Ising model CFT, but what's interesting about it for me is that it's preserved by an RG flow generated by this relevant operator, O21, in the Katz notation. So we can make an RG flow which has Fibonacci symmetry the whole time. Okay? And now this Landau-Ginzburg model comes back. Okay? So this tricritical Ising model, this is the Landau-Ginzburg description is a single scalar field with a sextic interaction. And this lower order deformation is exactly the O21 deformation described in Landau-Ginzburg terms. Okay? So that gives us these 2 degenerate minima. But this RG flow, when we think about it from the CFT to this gapped phase, has Fibonacci symmetry the whole time. And we're going to use that to understand the spectrum. So what are we supposed to do? We're supposed to look at this strip algebra and understand its representations. There are 2 interesting elements of the strip algebra. I've written them here. So there's one which takes you from a soliton sector to a particle sector. And there's one which goes the other way, from a particle sector to a soliton sector. These maps are not isomorphisms. Right? They're interesting maps, but they're not isomorphisms. Okay? So what can we say? Well, the minimum energy state in the soliton sector is some soliton, and it has a CPT conjugate, which is an anti-soliton, going the other way. And this Fibonacci symmetry maps these onto a non-zero particle state, a state in this sector. So, in other words, the states soliton, anti-soliton, and particle form a triplet of equal energy. That follows just from the symmetry of this model. Okay? So let's visualize it in a quiver. The nodes are the vacua. We have two vacua. And the arrows are the excitations. So we have a soliton-anti-soliton pair. And we have here a particle loop. Now, symmetry alone does not predict for us the number of such multiplets. In this case, it's known to be exactly 1. That's the integrability answer. But in the integrability case, the fact that these have equal mass is some kind of miracle. For us, the fact that they have equal mass just follows from the symmetry. Okay, integrable examples are great, but can we use symmetry to understand something new? Let me now tell you about 2D quantum chromodynamics. So, for my last example, we'll be considering gauge theory with some gauge group G and massless fermions in some representation R. So at short distances, this is a model of free fermions. At long distances, it's a coset model. The numerator of the coset, spin dimension R level 1, that's the bosonized description of the free fermions. And the infrared is the gauge group at a suitable level. The denominator is the gauge group at a suitable level. And typically, that's a conformal field theory. But if the central charge happens to be 0, of this coset, then this infrared has a mass gap, and that's a topological coset. So that's the simplified setting that I'll be focused on here. And okay, we'd like to understand what are the massive particles, solitons, and their scattering. So one take-home message that you should know is that this kind of gap QCD always has an interesting fusion category symmetry C. One way to visualize this is from 3D. So if you want to think about the infrared, the bulk of the 3D is some Chern-Simons theory. And then it has coset boundary conditions. So you have this Chern-Simons theory on an interval with coset boundary conditions. And mathematically, what is the relationship between that construction and the fusion category symmetry of the problem? Well, it's again this Drinfeld center construction. So this Chern-Simons theory is the Drinfeld center of the fusion category symmetry of this problem. And that allows you to deduce what this symmetry is. Also important is that this symmetry C is spontaneously broken in the infrared. And that leads to multiple vacua and soliton sectors to study in 2D QCD. Okay, so now let's really do it. Let's apply this fusion category symmetry to deduce some constraints on the spectrum. Here's the simplest example. SO3 gauge theory with matter in a symmetric tensor, so the 5-dimensional representation. Here's the relevant bulk TQFT. Okay. Now, this coset the relevant coset has vanishing central charge, so this is a gapped theory in the infrared. And the fusion category symmetry consists of 3 lines. So there's the identity, there is a Z2 symmetry, which I called V, and there is some non-invertible symmetry A. These are their fusions. This is the non-invertible symmetry fusion rules. This symmetry is spontaneously broken in the infrared of this gauge theory, and therefore there are 3 distinct vacua. This symmetry breaking pattern permits 3 possible irreducible representations. And we can visualize them in 3 possible quivers. Here is one. You have 3 vacua and lonely particles dancing above each vacuum. Here's another where you have now a soliton pair. And here's a more intricate pattern where you have soliton-anti-soliton between 2 different sets of vacua and also 2 stable particles. And a priori, symmetry does not tell us how many of each of these kind of multiplets exist. However, we do know that each superselection sector must be non-empty. And this tells us that the stable states must furnish a connected quiver. And so we can conclude that in this gauge theory, at least one of these has to be there. That's a non-trivial statement. In this gauge theory, I'm telling you about the existence of some particles and that they have equal mass to some solitons. Okay, let me conclude. What did I tell you? Non-invertible symmetries can imply novel degeneracies of massive spectrum. That's the main takeaway message here. They can relate particles and solitons, something that ordinary symmetries could not do. And this is a computable framework. There was a key role played by module categories. That was where we got all our technical power. And we can apply this in interesting examples. You know, 't Hooft solved the large color limit of QCD2, and half a century later, non-invertible symmetry is now giving us new tools to make progress at finite colors. Thanks very much.
Questions?
Is electric-magnetic duality at some particular coupling constant an example of this?
Thanks very much for the question. Indeed, that's an example where you have the particle-soliton degeneracy. Yes, in SUN Yang-Mills, electric-magnetic duality is a non-invertible symmetry.
What about in ordinary quantum electrodynamics, if it happens to have mono?
Like abelian gauge theory, you mean? I'm less sure about the answer in general to that case, but in the case where we know the duality, SUN, how it works, the reason it's non-invertible is because it changes SUN to SUN mod ZN. Right? So if you remember this fact, there's an interesting interplay of the duality transformation and the line operators in the theory. And that eventually leads to the symmetry being non-invertible.
Other questions?
You told us about this example of SO3 with R equals 5. Can you say a little bit more about patterns of the solitonic spectrum at finite n for other values of n? Are there interesting phenomena?
No, I mean, not yet. We've done a few examples, and we've worked out the representations in a few cases. It looks quite sporadic. The shapes of these quivers that you get more intricate and interesting. I don't yet know kind of a general pattern.
Very nice talk, Clay. So in the context of conformal field theories, these non-invertible symmetries in the form of Verlinde algebra give us insights about modular transformation properties as Verlinde showed. Now you're deforming away from the conformal point and you're still preserving some of the structure. Does that teach you something about the partition functions or modular transformation properties of the masked up version of CFT in some form?
I think the answer should be yes, but I don't have like the sharp formula for you. Yeah.
Just a quick comment to Lenny's question. I thought in QED, in free Maxwell, right, a special point of the coupling constant, then there are also non-invertible symmetry.
Certainly, absolutely, that's right. Thank you, but I thought he was asking about the case with dynamical states. Yeah.
Maybe there's time for one more question. Okay, if not, let's thank Clay again for the. So our next speaker is Shu-Heng Shao.
Is it on yet? Okay, great. All right, well, first I would like to thank the organizers for running this wonderful conference and giving me the opportunity to speak here. So today I'll talk about two papers I wrote with two truly excellent graduate students from MIT, Arko and Sal. The talk will be mostly based on the first paper. If time permits, I'll talk about the second one, which is related to T-duality. All right, so let's get started. So in recent years, we have seen a lot of development on generalized global symmetries, both in continuum quantum field theory and in discretized lattice model. We have heard a lot of discussions from yesterday and also in Clay's talk. Now, this arises from an interdisciplinary collaboration between high-energy physicists, condensed matter physicists, and also mathematicians. Given this development, I believe the time is right to revisit an old topic, namely lattice chiral symmetry. It's an important question because, among other things, our nature is chiral. There are many existing proposals and constructions with various pros and cons. There are no-go theorem. I'm not going to review every aspect of this story, but I'll take a particular direction to approach this question. More specifically, the question that we would like to discuss today is, given a continuum quantum field theory, this is our target, can we realize its chiral global symmetries and their anomalies on the lattice? To approach such a question, the simplest setup you can possibly imagine is a free massless Dirac fermion in 1+1 dimensions. So Dirac fermion in 1+1D has two complex components, psi left and psi right. Psi left is a one-component, complex, left-moving Weyl fermion, similarly for psi right. This is the Lagrangian. I believe everyone in the audience has seen this Lagrangian before. We use it all the time on the string worksheet, etc. There's no hidden component. Psi left is one component, same is true for psi right. Okay, so the left and the right fermions don't talk to each other, and we have two U1s. The first one is a vector U1 that rotates the left and the right by the same phase. The second is an axial U1 that rotates the left and the right by the opposite phase. Globally, there's a Z2 quotient. That's not terribly important for my story, but I figure I should mention it. Importantly, in the continuum, the vector and the axial U1s commute with each other. These are phases, right? Phases commute. All right, so now you would like to put it on a lattice. I'm going to work in a Hamiltonian lattice formalism. That means my time is continuous, and I'm later on going to give you a Hamiltonian describing the continuous time evolution. On the other hand, space is discrete. Specifically, my space is a one-dimensional spatial lattice with L site on a closed ring, labeled by this index J. A Dirac fermion in the continuum has two complex components. So naively, if you want to regularize it on the lattice, you put two complex fermions on every lattice site. But then you immediately run into an issue. That's the famous fermion doubling problem. In the continuum, the dispersion relation is linear. But on the lattice, the dispersion relation is necessarily periodic in the lattice momentum. The simplest periodic function you can write down is sine. And at this end of the momentum of the Brillouin zone, you get a very good approximation of the linear dispersion relation, and you get a right-moving fermion. But at the other end, it has to bend around, and you get a left-moving fermion. So the upshot is that you buy one and get one for free. Left and right always come in pairs. So if you naively discretize your fermion by putting two complex fermions at every site, in the continuum limit, you get two Dirac fermions, and that's twice as many as what we are shooting for. There's an obvious fix for this issue. Instead of putting two complex fermions per site, you put one complex fermion per site, which I denote by Cj. So every site, I have Cj and its dagger, and that's all. I'm not putting any more fermions at every site. They obey the standard anti-commutation relation. Upon quantization, each site gives you a two-dimensional Hilbert space. That's a fancy word of saying a qubit. You have L sites, so the total Hilbert space is 2 to the L dimensional. Okay? So I have given you the Hilbert space. I have given you the local fermionic operator that acts on the Hilbert space. Now I have to tell you the Hamiltonian that will eventually flow to the desired quantum field theory that I'm shooting for. And that's the standard stagger fermion Hamiltonian that has been considered by Banks, Kogut, and Susskind in a series of works back in the 70s. And I'm going to start with the simplest possible stagger fermion Hamiltonian. It involves nearest neighbor interaction. It doesn't get simpler than that. And I want to preserve at least one U1, so everything comes in pair of CC dagger. The continuum limit, as I mentioned, is a single free massless non-chiral Dirac fermion. I should emphasize that the quantum field theory that I land on is non-chiral. It has both the left-moving and the right-moving fermion. But I'm going to discuss its chiral global symmetries. All right, so let's take a look on the symmetries of this lattice model. Obviously, there's a manifest U1 vector symmetry that just rotates all the complex fermions by a common phase. But when we put one complex fermion on every lattice site, what we secretly had in mind is that we take the two components of the continuum Dirac fermions, take one component, put it on the even side, take the other, put it on the odd side. But because of that, you mess up the axial symmetry. And therefore, by staring at this Hamiltonian with naked eyes, you only see one U1. And the central question we would like to approach today is, where's the axial U1 symmetry in this lattice Hamiltonian model? Okay. Now, common lore states that it's difficult to realize the axial U1 symmetry on the lattice because of an anomaly. More specifically, I had in mind the 't Hooft anomaly between the vector and the axial global symmetries of a Dirac fermion. That means you cannot simultaneously gauge both the vector and the axial symmetry. In other words, it means that the axial global symmetry is broken when you gauge the vector global symmetry, and vice versa. This is really the oldest anomaly known to humanity. It was first discussed by Schwinger in the late 50s, but I think it was really clearly spelled out in a paper by Ken Johnson in the early 60s. Note that this predates the famous ABJ paper in '69, and this is in 2D. In equations, it means that the axial Noether current is no longer divergent free when you activate the electric background gauge fields for the vector symmetry. Perturbatively, this is captured by a one-loop 2-point Feynman diagram. And perturbative anomalies are known to be challenging to realize on a lattice, especially with a finite-dimensional local Hilbert space. And that's the case for us. On every local Hilbert space, on every site, we have a qubit. That's two-dimensional. Having said that, it is actually possible to realize this anomaly, more precisely the bosonized version thereof, using infinite-dimensional local Hilbert space. I'm not going to talk about this construction. In fact, many people who have worked on this subject are here in the audience. Today, I'm going to work on lattice model with a finite-dimensional local Hilbert space. So coming back to this talk, let me give away the punchline first, and then I'll go to the details. The punchline is that take this simple Hamiltonian. It not only has a manifest vector U1 global symmetry, it also has an exact axial U1 global symmetry generated by an axial charge QA. Both QV and QA commute with the Hamiltonian, so they lead to conserved quantities. Both of them have integer eigenvalues when acting on this Hilbert space. This is an exact finite L, finite lattice statement. If you look at each one of them, it generates a perfectly ordinary U1 global symmetry on the lattice. It maps local operator to a local operator. It fits all the bill that, say, John presented yesterday. But there's always a but in theoretical physics. On a finite lattice, these two exactly conserved lattice charges do not commute. And this is to be contrasted with the continuum counterparts, where the two U1s do commute. Okay, so that's the punchline. Now I'm going to get into the details. This is usually the point where people take up their phones and check the emails, but please bear with me for the following few minutes. I'll try to make it as entertaining as possible. All right, so let's take a look at the continuum symmetry again. We have a vector symmetry and an axial symmetry. The basic observation we are going to use in 1+1D is that the axial charge in the continuum is actually related to the vector charge by conjugation. And the operator you conjugate by is a charge conjugation symmetry, CR. What does it do? It acts as charge conjugation only on the right movers, but not the left movers. As you can see, if you swap side right with side right dagger, you exchange the vector and the axial symmetries. Since we already have the vector charge on the lattice, now it suffices to find the lattice operator that eventually flows to this charge conjugation symmetry in the continuum limit. So how do we find it? Well, the trick is to think in terms of the Majorana fermions. So on the lattice, we're going to decompose every complex fermion, which I denote by Cj, into two real fermions, Aj and Bj. Aj and Bj obeys the Clifford algebra. The Hamiltonian now decouples into two real fermions. If you think about it, it's kind of funny. I don't know about you guys, but when I first learned math, I first learned real numbers and then complex numbers. But in physics, we actually learn Dirac fermion first, and then Majorana fermions. Of course, for good physics and math reasons. But for today's talk, it's actually very important that we view everything in terms of the real fermions. As you take the continuum limit, as we were discussing earlier, the CJ, this one-component complex lattice fermion, gives rise to a left-moving mode and a right-moving mode. And I similarly decompose the Weyl fermion into two Majorana Weyl fermions, the left-moving guys and the right-moving guys. The lattice fermion A becomes two Majorana Weyl fermions. The lattice fermion B becomes two Majorana Weyl fermions. The charge conjugation symmetry, in terms of the real fermions, flip the sign only of BR. Out of these four guys, it only flipped the sign of a single right-moving Majorana Weyl fermion. So how do we find the lattice operators that in the continuum limit that does the job? Well, the most naive thing you would try to do is to flip the sign of this lattice fermion B, but that's no good because B gives rise to B left and B right in the continuum limit. That's not what you want. Well, but for anyone who has worked on lattice fermions in the past, it should be obvious what the answer should be by now. The answer is lattice translation. But it's important that it's a lattice translation only acts on the B fermions, but not the A's. So let's focus on the B fermions and look at the dispersion relation. That's the sign function we encountered earlier. At one end of the Brillouin zone, you get a left-moving fermion. At the other end, you get a right-moving fermion. The hero of the story is a Majorana lattice translation operator, which I denote by TB. The subscript B means that it translates only the B fermion, but not the A fermion. This is a symmetry of the Hamiltonian that we are looking at. As is well known, when you go to momentum space, the translation operator now becomes diagonalized. It acts by a phase. And this phase is approximately +1 at one end of the Brillouin zone, and it's approximately -1 at the other end of the Brillouin zone. And that's exactly the operator we're shooting for. It only flipped the sign of a single Majorana Weyl fermion in the continuum limit. So I claim that this Majorana lattice translation operator TB flows to the charge conjugation in the continuum limit. That's to be contrasted with a lattice translation that shifts both the A and the B fermion at the same time. That's not the operator we're looking for. All right, given that, we can mimic this continuum relation to define a lattice operator QA by conjugating the lattice vector charge by this Majorana lattice translation. The vector charge takes this form in terms of the real fermions, and therefore the axial charge takes this very simple form. By the previous argument, it flows to the continuum axial charge. Let me list the nice property of this axial lattice charge. I'm not going to give the derivation, but every property is very simple to derive. First, it commutes with the Hamiltonian. Second, it is quantized. It has integer eigenvalues. So when you exponentiate it, it gives you a perfectly normal U1 global symmetry. Third is a sum of local terms. Each local term is this AJ, BJ plus 1. So you not only have the notion of a conserved charge, axial charge, you also have a notion of a lattice axial current, Noether current. Finally, when you exponentiate it, the way it acts on the fermion is completely local. It's not on-site in the sense of Shay-Chen's talk, but it only maps a fermion at site J to its neighbors. It doesn't spread out. It involves at most 3 fermions. So that sounds all good and rosy, but as I already alluded to, the new feature is that the vector and the axial lattice charges don't commute, whereas in the continuum, they do commute. All right? If they don't commute on the lattice, we should ask, what kind of algebra do they form? It turns out that this QV and QA generates the Onsager algebra on the lattice. This is the same non-abelian algebra that Onsager used in 1944 in his original paper solving the Ising model. Let me give you the presentation of the Onsager algebra. Its elements you have 2 integer sequence of operators, Qn and Gn. These are the definitions. The details do not matter. But as you can recognize, the first of the Qn is our vector charge. The second one is our axial charge. The only thing you need to know about this non-abelian algebra is that starting from our vector and axial symmetry, by taking repeated commutator, you generate the entire Onsager algebra. The G operator is the commutator between the Q's. And you can show that in the continuum limit, this goes to 0. And therefore, the vector and the axial symmetry commute in the continuum limit. All right. So let me summarize a little bit. This is the axial charge. It's quantized. But the only bad news is that it doesn't commute with the vector charge. We try very hard looking into the literature to see if anyone has discussed this quantized axial charge in the literature. We found this paper from 30 years ago. When we found it, it had 2 citations. Both citations were self-citations. So I think this is a paper really forgotten in the history by all definitions, but it actually briefly mentioned this interesting axial charge in the stagger fermion. Now, you could be a person who is really religious about the fact that vector and axial symmetry should commute. Well, in that case, there's also something for you. There's a different axial charge, which I denote by tilde QA. It also commutes with the Hamiltonian. And furthermore, it commutes with the vector charge. This charge was already discussed in the paper by Banks, Susskind, and Kogut in 76. But the price you pay is that it's not quantized. Both QA and Q tilde A flow to the same axial charge in the continuum limit, but it seems that we do not have a lattice axial charge that is both quantized and commutes with the vector charge. And it would be interesting to better understand the relation between this and the Nielsen-Ninomiya theorem. We have some preliminary thoughts, but let me not say more about it. Great. So we found the axial symmetry on the lattice. What can we say about it? What can we learn from this? So far, I only talk about a single Hamiltonian. But you can ask, are there other Hamiltonians also commute with both the vector and the axial symmetries? And the answer is yes. There are infinitely many such Hamiltonians commuting with both the vector and the axial symmetries. But then what are the consequences we can derive from these 2 symmetries? In this paper, we show that any Hamiltonian that commutes with both QV and QA must necessarily be gapless. So it could be described by a conformal field theory in the continuum limit or some non-relativistic scale invariant field theory. This is very reminiscent of the consequence of an ordinary perturbative anomalies in continuum field theory. But I will hesitate to call it an anomaly on the lattice. Conventionally, we define anomaly as an obstruction to gauging the global symmetry, as John defined in his talk yesterday. Here on the lattice, we have an Onsager algebra, which involve highly non-local charges. I don't know how to gauge it, but what I can say for confidence is that this lattice symmetry has similar consequences as an ordinary anomalies does in the continuum limit. Let me just give you a quick look on a 2-dimensional slice of the phase diagram, preserving both U1V and U1A. The entire phase diagram is gapless, but there are some interesting transitions between them. There are also some interesting WZW model points. Ask me later if you are interested in this phase diagram. Okay, so I'm at a string theory conference, so I should also say something related to string theory. You can bosonize this stagger fermion model, and you will find the XX model of Pauli's qubit. This flows to the C=1 compact boson CFD at a specific radius. The previous construction under bosonization mapped to an exact lattice momentum U1 symmetry and an exact lattice winding U1 symmetry, which has been discussed in these papers. And they also generate a non-abelian Onsager algebra on the lattice. Given that you have both the momentum and the winding symmetry on the lattice, it's natural to ask, is there a T-duality in this simple Hamiltonian lattice model? And the answer is yes, and it's in fact associated with a non-invertible operator, D. It exchanges momentum with winding with an important factor of 2. All right, let me summarize my talk. So for the most part of the talk, I focus on this Hamiltonian, but there's an infinite dimensional generalization of the standard stagger fermion Hamiltonian that enjoy both the vector and the axial symmetry. The punchline is that in addition to the manifest U1 vector symmetry, the lattice model actually has an axial U1 symmetry as well. However, they do not commute on the lattice, and they generate the Onsager algebra. The Schwinger anomaly of the continuum Dirac fermion field theory emanates from this non-abelian Onsager algebra on the lattice. This is a very novel mechanism for how anomalies can match. Usually, the way anomalies match is that, say, I have a SU2 global symmetry in the UV, it has some anomaly. I have a SU2 global symmetry in the IR, and it has to have the same anomaly by the 't Hooft anomaly matching argument. Here it's entirely different. In the IR, I have U1 vector times U1 axial with a Schwinger anomaly. In the UV, I have some infinite dimensional non-abelian Onsager algebra, but somehow the anomalies have to match. And it will be interesting to understand how that works in detail. Finally, this two symmetry force the Hamiltonian to be gapless, reminiscent of the consequence of ordinary perturbative anomalies. There are several outlook future directions to better understand the Nielsen-Ninomiya theorem. And can we realize more general chiral symmetry on the lattice? For instance, non-abelian chiral symmetries. And more interestingly, related to Clay's talk, do we have some hidden symmetries in lattice QED and QCD? In particular, there's a recent paper by this group of people pointing out an interesting relation between the lattice mass and the continuum mass in the Schwinger lattice model. It would be interesting to revisit that mass shift formula using the axial symmetry we discussed in the talk today. And finally, perhaps the most intriguing question is, how much of this generalized to higher D? Okay, with that, I thank you for your attention.
Questions?
Hi, Shu-Heng. Thanks for a fantastic talk. Could you say a little bit more about, I didn't get, you flashed this statement that in the continuum limit, these charges commute, but I didn't fully understand how that works.
Yeah. So let me say what I meant by that statement, this one, right?
That's
So
right.
what I meant by continuum limit is that you take a large but finite L. Then you still have a finite dimensional Hilbert space, but you pay your attention to the low-lying state. You look at those states, and you see how various operators act on this low-lying state. Say you keep the first 20 states in your Hilbert space. And then you take L, the number of lattice size, to infinity. And you see how G acts on this low-lying state. The statement is that G acts as 0 in that thermodynamic limit.
I see. So you're saying that that states that the Hilbert space kind of
Yeah, these are the states near the two.
the charges don't commute. The part of the Hilbert space somehow has infinite energy or something in the continuum limit.
That's right.
That causes
That's
it
right.
not to commute.
In the continuum limit, you only see states around here and around there. And G acts as 0 near those two corners.
I see. It's this middle section that makes them non-commute.
Exactly. That's exactly right.
Thank you.
So if you couple the vector theory to a gauge field, can you explicitly see that the time derivative of the axial current is equal to the electric field?
Very good. So you can ask the question so I have two charges, QA and Q tilde A. For this one, the one you study in your paper, you can see that very explicitly. It's I think you guys almost did the calculation. It's like a one-line calculation. So you can see something analogous to the anomalous equation that I presented in the first part of the talk. For the first one that I talk about, the story is a little bit more subtle. It breaks down at the earlier level. The reason is because QA does not commute with QV. So the moment you gauge the vector symmetry, this QA doesn't even commute with the Gauss law. So it's already meaningless to talk about QA the moment you gauge QV. It's very analogous to have a SU2 global symmetry. And I gauge a U1, and say in the Z direction, and ask what happened to the X direction U1.
Got it. Thank you.
Other questions?
So suppose you considered several Dirac fermions, so then you'd have non-abelian axial and vector symmetries. Is there any hope of finding a setup where anomaly-free chiral symmetries can be gauged?
The honest answer is something that's very high on our to-do list. We don't know yet. We are very interested. For instance, we're interested in the 3450 symmetry if you have multiple flavor of Dirac fermions. But the short answer is we haven't analyzed those yet. I secretly hope so.
Hope so.
Yeah.
Other questions? Okay, if not, let's thank Shu-Heng again for the
Thank you.
So our next speaker is Sulejmanpasic. Hope I didn't.
It's good enough.
Okay.
Hello, everyone. It's a pleasure to be here. Let me just get a moment to figure out. That's the laser. Good. It's a pleasure to be here. I had the pleasure to be invited here actually by Leonardo. I took a string theory course with him, and after that I thought I'm done with string theory. But much like Chuck Norris, you're not done with string theory until string theory is done with you. So I was asked to give a talk about this work, and I have to tell you, this is the mastermind of these two papers, Theo Jacobsen. He's a very bright young postdoc. He was a student when he approached me and asked, can this be done? All I said is, I think so. And then he did everything else. And I'm just sharing the credit. So what I want to talk to you is how to put Chern-Simons theory on the lattice. And I don't think we gave a complete answer, but it seems to be the right direction. And I want to just remind you about the Abelian Chern-Simons theory in continuum and some features that it has, which this audience probably knows very well. One thing is the basic observables are, of course, Wilson loops, and they're topological. There are some phases associated with their linking, ZK phases, where K is the level of the Chern-Simons theory. And there is some topological spin, which are the 2K phases, which you should really think of these Wilson loops as some kind of strips. And they can self-link, and there are phases associated with these little twists of these strips. And for a long time, I wondered, how would the lattice formulation of this function? And I always thought that somehow naturally these features, especially these little strip features, should arise. And I'm happy to report that it does in some way. But there are many subtleties, and of course people try to do this for a long time. And they basically had the answer. It just something stopped them, and I'll try to explain what. So I'll just give you an overview. So the first hurdle that you might think, and this was, I think, one of the reasons why we could do this now, is if you want to focus on a U1 lattice gauge theory, and if you try to put it on the lattice, the conventional way of putting any gauge theory on the lattice is to define some kind of group-valued objects on links. These I label with these U's, and then construct little plaquette actions by taking these U's around the plaquette, like here, and constructing some gauge invariant object. If this was a non-abelian group, I would also take the trace to make it non-gauge invariant. But in this case, these are just U1 phases. And then you can construct from this basic plaquette action, you can construct the full action, for example, by taking complex conjugate, because you want the action to be real. However, this kind of approach is well known that when you do this, the theory you construct kind of has no, in the modern language we would say that it doesn't have a magnetic symmetry, which means that it has dynamical monopoles. And the physical reason is that the lattice is kind of hollow, so you could always sum over configurations which corresponds to a monopole being inserted somewhere inside the cube. And this is bad news for Chern-Simons theory, because if you have a monopole in the continuum, a monopole is not gauge invariant, so you really don't want to sum over monopoles. So that's one problem. And the solution to this problem came in in the form of what today is known as modified Velan action. And to motivate the Velan action, you can take this usual, which is called Wilson action. You can write it as cosine of dA, where A is the is the phase here of well, the exponent in the phase. And when you take beta to be very large, then you can do then you can just keep the quadratic term here. And when you keep the quadratic term, you have to also tag it with some minima of the cosine, which are some integer valued things. And this is known as the Villon model. And I think I gave some updated slides, but there was something is missing here. But the whole point is that there is a gauge symmetry which shifts this A, which is supposed to be a phase, by 2 pi times an integer. And you can absorb this shift by the shift of n, appropriate shift of n. So there's some kind of a discrete gauge symmetry in this formulation. But although n itself is not gauge invariant, dn is gauge invariant and corresponds to something physical. And what it corresponds to is that if this dn, some kind of an exterior derivative of this plaquette-valued integer field, is non-zero, that's interpreted as a monopole. And so what me and Christoph Gattringer did in 2019 is we just imposed this constraint that it's 0. We introduced some Lagrange multiplier, which has an interpretation as a dual magnetic field, if you will, and project out monopoles. And so this became Shu-Heng and Seiberg and these people actually called it modified Villon formalism, which is what it's known as today. So this has a multitude of features which are very interesting. I won't go into it. This is an incomplete list with incomplete references. But people find it useful for all kinds of things. I was involved in some of this research. But this solves the problem, at least in principle, of eliminating monopoles from a U1 lattice gauge theory, and then maybe gives hope of formulating a Chern-Simons theory on the lattice. So just to repeat, the ingredients of this Villon formulation is some kind of real valued now. Now these phases can be thought of as real. These A's are real valued and some integer valued plaquette fields. And there is some kind of a gauge symmetry which corresponds to the fact that A is really supposed to describe an angle, some kind of redundant description. So let me now just mention a couple of how to discretize the Chern-Simons term, the relevant Chern-Simons term, without thinking about this global aspect. So now for the next couple of slides, I'm going to ignore the fact that A is supposed to be some kind of an angle, and I'm going to fix that later. But there's another layer of complication with Chern-Simons theory, and that comes from when we try to discretize this continuum formulation, and immediately there's an ambiguity here because we don't necessarily have to take this gauge field at the vertex, for example, starts at the vertex here. This is supposed to represent this AX mu pointing up, for example, and it's multiplied by some kind of a flux, which is represented by this plaquette, but we don't have to take it on this end. We can take it on this end, or we can take it on a plaquette next to it, and so on. So there are ambiguities of how to do this, but you want to do it in such a way that it's gauge invariant. And by gauge invariant, I mean that if A is shifted by some total derivative, again, I'm not thinking about A being compact in any way, just the most naive total derivative, some small gauge transformation, if you will. So this is what I mean by gauge invariance. To motivate how one can construct gauge invariant actions, imagine that for the moment we have A field, which is some kind of field on links of the original lattice, and B fields now live on plaquettes of the dual lattice. Then there's a natural product between these two objects
by the intersection, right? Whenever the plaquette of the dual lattice intersects the link of the original lattice, we can make a product. And moreover, if we now do a gauge transformation of A, let's say that A gauge transforms somehow by a total derivative, one can show fairly easily that you can do some kind of partial integration, and I think I missed a sign here, but it doesn't matter, onto B. So if B is closed, then this will be 0. Okay? So then when you have a cubic lattice, you can simply take, because for us both this dA is supposed to play the role of B, which is on the original lattice, and A is also on the original lattice. Nothing is on the dual lattice, but you can simply just shift the original lattice to the dual, or the other way around, and correspondingly define a product between these two, the fields which all live on the same lattice. Which actually is exactly what mathematicians would call a cup product. It's an analog of the wedge product on the lattice. But there's an ambiguity here because you pick a particular direction. So for example, in this case, I picked diagonally in all directions, positive directions on the lattice, 3 directions on the lattice. I picked diagonal this way, but I could have picked any other diagonal, and it would be perfectly fine. So there's this ambiguity, and I want you to remember this ambiguity in defining the cup product, because it will kind of be important later. It will have something to do with Wilson lines becoming strips. So what I wanted to say is that by defining a cup product in this way, then we automatically have this gauge invariance. But now we want to make this A compact. And to make it compact, we need to force A to have some kind of gauge symmetry, such that if we shift A, this real number A, by 2 pi times an integer, that's an invariance. And we can do that locally on every link individually. And in order to construct such a theory, we oh no, there's a problem, which I forgot apparently. I will do that in a moment, but I want to emphasize one more problem, and that's the problem has to do with the fact that if you write an arbitrary action in momentum space involving gauge fields, and there's some kind of a G function of momenta here, then one can show in this model with this cup product, or in fact one can show that it's universally true if you insist on gauge invariance, that there are some kind of zeros which are not associated with the usual gauge symmetry of this G function, which appear when all momenta add to pi. Okay? And this was a big obstacle, I think, for many of you. You see this result is in 89, and this was known for a long time. But and as I will show in a moment, is that this is related to some kind of a weird symmetry, which simply just kills all Wilson loops. So, and the result is really general. You may think, well, maybe if we defined the cup product in some other way or did something very fancy, we can avoid it. But it seems to always be there. So there are these extra zero modes which, for which the quasi-momenta obey this relation. In fact, if you look at the model we had, these extra zero modes are related to the symmetry, and the symmetry goes something as follows. If we just shift A's by an epsilon, local epsilon here, arbitrary epsilon, then you can see that the action changes by this amount, where there is this combination of the cup product, epsilon cup x plus x cup epsilon.
And one can convince oneself that you can make this vanish, you can make this combination vanish, as long as you take that epsilon, this x is some combination of a and epsilon, doesn't matter what it is, but as long as you take that epsilon is such that, for example, I take epsilon to be alpha on one link, and then I take it to be minus alpha on a link which is translated diagonally. And then I take it to be plus alpha and minus alpha and so on, okay? As long as I stagger the transformation like this, and it can be alpha on this ray and a completely different beta on another ray, and it can be a gamma, for example, on these links. So you can basically, you have huge amount of symmetries, some kind of subsystem symmetries. There's symmetries only on rays which go in diagonal directions. This is what causes these extra modes to appear. You can see it has something to do with pi. I said all momenta add to pi because you're staggering everything. You're staggering, it's plus, minus, and that's where why it happens at the end of the Brillouin zone where all momenta add to pi. But you see, such a symmetry forces all Wilson loops to, almost all Wilson loops to vanish, because let's say that I have a Wilson loop like this. It is charged under this symmetry because it touches only one of these alphas and doesn't touch a link where there's a minus alpha, so nothing cancels. Or even an elementary Wilson loop is charged under this alpha symmetry and also touches these three links which have their own symmetries. So most Wilson loops just simply vanish. And this symmetry is really a one-dimensional symmetry. So it cannot be spontaneously broken. Right? So you may ask, well, maybe something survives because they're somehow spontaneously broken. The whole thing looks very bizarre, and that put off, my impression is that put off research in this direction for a while. But I'm going to ignore it for now and just press on, try to construct a theory which is a U1 lattice gauge theory of some kind, okay? And see if we can interpret it to be a Chern-Simons theory. So to do that, as I said, we have to make the action, sorry, this is supposed to be capital A here, not a small a. It's the same gauge field. So we have to force this A to be an angle. And in addition, it should also have this small gauge symmetry, if you wish. So it should be possible to shift A by 2 pi an integer. And we can absorb that shift by introducing some plaquette integer field on plaquettes and just absorb that change here. And you can check that as long as k is even, then this action is invariant, or rather it's 2 pi times an integer, which means when you exponentiate it with an I, the weight of the path integral is invariant. Now, in continuum, k can be also odd, but these are spin Chern-Simons theories, and we realize we can also treat these, but we have to introduce some kind of a fermion. I won't go into it. It's not very important for my talk, but it can be done. For the moment, I'm just going to keep k even and continue with that. I should emphasize that we could also impose remember, n has to be closed because we don't want any monopoles. We could introduce a Lagrange multiplier to impose this. But it's easier just to think of n as obeying some kind of constraint and not clutter notation. But there's some utility in putting a Lagrange multiplier because then you have monopole operators. They're not really gauge invariant in this case, but there's some interesting features there too. Okay, so now let's try to analyze the properties of this theory and see whether it has anything to do with Chern-Simons theory. The common lore in the literature seems to be that because of these extra zero modes, nothing is the same. And people even told us that this model is clearly critical. It has some, if you look at correlation functions,
you will just find gapless states. So let's analyze it. So first thing is that it has a Zn one-form symmetry. One can show that this corresponds to a shift of A by 2 pi over n times some integer omega, such that omega is closed. So that's good. It has a Zn one-form symmetry, just like in, sorry, I meant Zk, of course. Here, Zk, one-form symmetry. And this is supposed to be K. It has also an appropriate Hooft anomaly. I won't have time to show it, but one can try to put background fields for this one-form symmetry and show that, that you cannot put background fields such that they're gauge invariant. And you reproduce the anomaly of the continuum. So as Shu-Heng mentioned, this is not always easy to do on the lattice, but in this case, it drops out. Now, it still has a staggered symmetry, which causes Wilson loops to vanish. So we have to address this. And this is the last bit that really needs comment. So as I said, a charge 1 Wilson loop like that, a straight one, which, for example, is charged under the Zn symmetry, Zk one-form symmetry, vanishes by the fact that there's this exact symmetry, which is not spontaneously broken. But if I spread the charge 1 Wilson loop by putting a charge half here and a charge half here, then you see this staggered symmetry here transforms as alpha here and as minus alpha here. And this thing, this object here, is not charged under the staggered symmetry. Now, of course, charge half Wilson loop is not usually gauge invariant, so it's actually attached to a surface, and these plaquettes are tiled with this n field to make everything work out correctly, and all gauge symmetries of this object are satisfied. I mean, everything is invariant. So now you see these are strips now. And these actually turn out to be the charges of the Zk. Again, sorry, I systematically put this in. It's too much working with SUN gauge theories. These strips turn out to be the charges, the topological charges of the Zn symmetry. And they're guaranteed to be topological, these strips precisely. And further, you can leverage the Hooft anomaly and show that, that all the correlation functions of, by doing gauge transformations of the background field, that is equivalent to deforming these strips into arbitrary shapes. And this gauge transformation is almost exact, except when strips cross each other. Then you get some phases due to anomaly. And then you can show that correlation functions like this are true, like what we said in continuum is supposed to be. And you can even show that there are some kind of twisty striped Wilson loops, which you can think of as this garden hose loop, that is equivalent to the straight Wilson strip up to a Z2K phase. And this is the topological spin. But you can ask a question. You can now ask a question whether there is something more. Okay, we found some topological sector. It seems to have reproduced everything we know in continuum. But you can ask a question, okay, what about these extra zero modes? Are there some correlators which are gauge invariant correlators, which are maybe not charged under this staggered symmetry, so they don't vanish, but are critical, are somehow long-ranged. And you could generally write any kind of operator which is gauge invariant by writing this combination. Again, this is supposed to be capital A. This combination is gauge invariant under all gauge symmetries, even this discrete gauge symmetry. And you can put some kind of source H here, and you put it in this form. You say H cup this combination cup H, guarantees that it's neutral under the staggered symmetry, under this weighted symmetry. Indeed, this staggered symmetry comes exactly from the fact that this cup product doesn't really commute or anti-commute, unlike the wedge product.
in continuum. So this is a general kind of generator of correlation functions. But when you put this in, you can easily show that by shifting A, the gauge field A, by this H, you can just remove this. So nothing there are no non-trivial correlation functions in this model. So these extra zero modes don't seem to be dangerous, at least not from the point of view of bulk. So let me summarize with some comments before I conclude. So the system can be quantized also canonically. We did this in a different paper, me and Theo. And still similar staggered symmetry persists, but in the Hamiltonian formulation, it actually is connected to a constraint. So it really should be interpreted as a gauge symmetry, okay, which forces Wilson loops to vanish. It's an exact gauge symmetry. It's an exact constraint on the Hilbert space in the Hamiltonian formulation. You can actually relax this by introducing a Maxwell term. When you introduce a Maxwell term, the staggered symmetry is gone, and this constraint is gone also on the Hilbert space. And that's another way to regulate the theory. And in some recent papers by a Beijing group, Jingyuan in particularly, and some other people, which are, I think, scattered all over, were looking at such constructions. These people here were looking at the canonically quantized system with Maxwell term, and here it was a space-time lattice. And in this paper in particular is interesting. They are claiming that in order to understand the gravitational anomaly and the edge mode, you need to introduce this Maxwell term. And in continuum, indeed, you need to gauge fix and introduce a metric in order to quantize Chern-Simons theory, as Edward pointed out a long time ago. And then you find this gravitational anomaly. When you introduce a metric, there's some very weak metrics dependence. So in a similar spirit, these people here said, well, Maxwell term is needed, and then it lifts this staggered symmetry, and some things are a little bit easier. But everything I said still persists, and everything becomes, the topological Wilson loops are still strips and so on. And in this same paper, they make some claim about gravitational anomaly, but I don't fully understand it, and I think there may be some issues here, and this was asked to us by many people, so if you have a question, I'm happy to take it, but don't be disappointed if I don't have a good answer for you. You can ask me. And I just want to conclude with this preliminary result, which it's not published yet, but in the Hamiltonian formulation, we put now a boundary on this same theory, but we had to introduce a Maxwell term because things are much easier. I don't know if it can be done without Maxwell term. When you introduce a Maxwell term and you put a boundary in the Hamiltonian language, indeed, you seem to have some kind of an edge mode here, which at the boundaries, Shu-Heng mentioned that the edge mode on the lattice what goes up has to come down. But here it doesn't really have to come down because there's a bulk spectrum, and this just fuses with the bulk spectrum here and here on the two ends. So everything seems to be consistent with the continuum. And this is my concluding slide. It more or less says everything I said so far. So with that, I would like to thank you for your attention and have us go get lunch.
We have time for some questions. Come here.
Thank you. Very nice talk. So this relates actually to the first session we had on symmetries, the question I have, which is the question I also had about the first session, what does it have to do with string theory, more specifically quantum gravity? And in my discussion with Mesam actually made a good point that I want connected to the talk that you're making. The point he made is that these symmetries, when you realize them in lattice models, have very similar features to quantum gravity conditions that we get. For example, when you have global symmetries on lattice, you always get all the full spectrum of charges that we expect in quantum gravity context and so forth. And it seems also that the point that Wen has made is that these lattice models seem to have very similar features to what we expect in quantum gravity context, surprisingly. It's as if you're describing quantum gravity, though you're not. You're talking about lattice models. So related to the previous talk and also your talk is the difficulty in lattice models to avoid having situations where there is gravitational anomalies. So, or anomalies in general to realize on lattices. And in your case, when you're talking about the U1 Chern-Simons, you can have a U1 Chern-Simons theory in continuum, but in lattice theory, the question is, can you actually have just a U1 Chern-Simons by itself, or do you have another U1 with the opposite level hidden in your model, which is my question to you. In other words, you will have a gravitational anomaly in your context if you just have a U1. The analog of having a chiral fermion gauge in your context is the analog of having a single U1 with just one chirality, with one level. Is it possible that in your model you also have another U1 with the opposite level?
I don't think that there's anything else in the theory. We looked at all the observables. And not only that, you see that there's a exactly chiral mode on the boundary. I mean, this is preliminary, but this Beijing group also looked at it was Maxwell. Okay, they added a Maxwell term, but that doesn't change anything except it makes things simpler. And they looked at the boundary, and they found this chiral mode, and we did in the space-time lattice. And we also find the chiral mode on ours. So I think that this is indicating that at least the system flows in the infrared to a system which has a gravitational anomaly. How that gravitational anomaly manifests itself on the lattice itself, I honestly don't know. Honestly, gravity is not my stronger suit, and I don't fully understand how to understand it on the lattice. But I don't think that there's anything preventing the system to flowing unless there's a no-go theorem that I'm not aware of, flowing into.
Thanks.
I mean, indeed, we know in condensed matter theory there are Chern-Simons, effective Chern-Simons theories. So.
Is there a natural non-abelian generalization of your constructions, or is that much more difficult?
Yeah, $1 million question. So, in fact, there are some, I know Natty Seiberg actually wrote a Chern-Simons on the lattice, non-abelian Chern-Simons on the lattice term, but it wasn't analyzed to my knowledge. And I think people simply got discouraged by the fact that abelian one doesn't work, so why wouldn't you even try? But there certainly exists in the literature something written down. I don't think it was analyzed. And I'm hoping that our work will motivate people to revisit these ideas, because I think it was unnecessarily abandoned in the past.
Any other question? Okay, if not, let's thank Tin again for the very interesting talk.
Two quick announcements. So now we break for lunch, but we come back here at 2:30. Okay. The second announcement is that there are also posters and also food in the building just across from us, A6. Right. A third of the posters are there. Okay. All right. See you after lunch.